Hey there, the unretired engineer coming at you again to talk about engineering and projects. And so today I'm going to be continuing a little bit on the topic of small business innovative research, the bit program that I worked on when I was working in the government, and then worked on some more when I was working for a small business after leaving the government. And so I have a little bit of a view of both sides of it. But today I'm going to be talking a little bit about the actually the from the inside when I was the technical program manager for a program that I had actually created the topic for, and then helped select the company that had proposed a solution. So going back, the last time I talked a little bit about a project that my boss predecessor had instituted, a delidding machine that where it worked almost perfectly. It basically was proposed, it was demonstrated. They actually built a unit, and the Navy facility I worked for used that unit for the next 15 years. They helped the company commercialize it by demonstrating it and using it to demo for companies. And they then went and sold those units and saved the government hundreds of millions of dollars over time. So it was a big success. And, you know, that was really how the program was supposed to work. They don't all work out that way, but if it doesn't work out that way, it doesn't mean that it wasn't a success. It just wasn't a success in the way that was maybe expected at the start. So the guy who proposed this had a small firm in Rochester, New York. They had so he was a PhD. He was a professor. I think he's taught controls and things like that, but he had his own little firm that he did work for various people for. So, and of course, in that region, which is where Kodak and IBM and RCA, a lot of other companies had lived and breathed in that area. So a lot of precision instrument region in that area. So it kind of made sense that's where it came from. He was an older gentleman. I am afraid I don't remember his name any longer, which is a tragedy. You know, he was old school, multi-domain controls engineer. He knew electrical, electronic, mechanical, pneumatic, hydraulic, and he did it from first principles. He did the calculations. He didn't use simulations. He basically knew how to run it all. But and he had a really deep background. He wasn't American. He had a pretty thick accent, but he was funny as heck. So I worked with him and with his son, who was probably a pretty late child, as he was relatively young in comparison to the professor. But the professor was one of those engineers who we see less and less of every year, in that he had deep domain knowledge. He had a lot of hands-on. He did things really from first principles, and he was very, very good at what he did. So the machine that we're talking about here is essentially, it's a printer, but it is a writing, or what I would call a writing system. So it took ink, and the ink we're talking about here are conductive inks that are usually printed through a screen on a screen printer. So the inks are optimized for that. They're a thixotropic, that is, they change their behavior as you run a blade across them. They actually thin as they're sheared to flow through the screen, and then when the screen comes away, it's left as a smooth, very consistent. And that was a business I was in. I was a thick film engineer early on. I was screen printing, and what we were looking for was a way to do prototype short runs very, very quickly and not have the wastage that came from doing that prototyping on a screen, where the screen, the material dries out because it's thin, spread across a big area. the ink, the fluids dry out, you can't reuse it. And so you have a significant amount of wastage when you move from circuit to circuit. So prototyping can be quite expensive, particularly in our realm where we were doing a lot of different things, but in small quantities. It made a lot of sense to look for a writing system that would allow you. So, but the problem is you don't really want to have to reformulate the ink. The inks are very tricky to formulate. They're optimized for a set of performances, and you don't want to change that, because if you change one thing, you change another, and that means that if a design that you came up with for screen printing wouldn't work on a writing system or some other method if you change the ink, right? So we wanted to be able to use the same ink, but that the thixotropic, the thinning with shear behavior made it almost impossible to use in any conventional writing system. If you simply put it under pressure, it would start to flow, it would start to shear in the tube, and then it was almost impossible to stop it flowing exactly when you wanted to do. But the machine that the professor came up with essentially had a cyclical pump. It would pump one direction, then the other, very, very precisely in basically infinitesimal amount of material per pump per cycle or control in those cycles. And it could stop and reverse very accurately because the system was fully sealed. It was able to actually snuff the material. It would reverse and instantaneously pull the material back. And then the pen tip would fly over the surface, basically floating on a layer of the ink being dispensed, and it would know exactly where it is. It would monitor it. It would then be, it actually was able to track if the substrate was bowed or wavy. It could see all of that and account for it as it was flying over the surface. And it would know when it's coming up to the end of a run. And instead of then just stopping and then blobbing, it would slow and then snuff. And it would have as precise an endpoint as you got with a screen print. It was a very good electromechanical system. It was essentially, you can call it a closed loop control circuit to control the fluid behavior. The mechanics worked elegantly, and it actually was very reliable as well. The problem really we are talking the late 1980s, right? So we're not talking the 2000s when software is all but a solved problem and controls at that level are all but a control problem. And he basically went to HP Instruments, bought instrument control systems and hooked them up to his equipment. And he did programming in HP Basic and HP Fortran to create a usable CAD system that you could do layout in. And it actually worked, the whole system. So he had done the demonstration, that all worked really well. He then actually built the complete system, and my facility got one. And I actually operated that system for years, doing a variety of things. So I got to learn that machine. There were issues, right? One was, we were going to save ink. Well, it didn't really save much ink because it was a single-headed system, and anytime you're talking about a thick film circuit, it almost invariably have a conductive ink, which is often gold or silver, and then you'll have resistive inks, which will be a variety of different resistive levels. And then you'll often have an overlayer, a dielectric layer, and that you would use. So there were 6 or 7 inks that we wanted to use and only one head, so you had to clean it. Now, it didn't use much, because it was a picoliter type control system, it didn't use a huge amount. You had to clean it all the way through. that was actually fairly onerous to make sure it was cleaned properly and then put back together and operating. So, and you were wasting all the ink in the system when you did that. So you saved some ink, but not a lot. And you now had a cleaning cycle, which was pretty onerous. Today, you wouldn't do that, right? Today, the system basically was so sealed that you could have put a cap on it and put it aside, had a different head, and just run that. And that would have been a reasonable solution. Today, you would almost undoubtedly go to a multi-head system and it would just, do the whole thing. But again, in that day and age, trying to do those things was much more difficult. Um, the other problem really was that the CAD system worked in simple geometries, and I could do the little tiny little circuits that we often fiddled with. I could do quite easily. Once you got beyond that, it was very, very difficult. And then you had the multi thing. So it really was a system that was probably ahead of its time technologically. It was technically very capable in that one thing, but if you, for the original use case, it really didn't solve the problem. It was actually easier to just make, new reticles, shoot the screen, and do the kind of the photo etching in the screen and make it that way. It was as easy to do that this system didn't really solve that problem. But the interesting thing is that there was a Navy system, and there was a problem, and the people who were having that problem were actually up there in the Rochester, New York area. They were working on the Navy's large phased array I'm sorry, not lasers, radars, and they were having serious problems. Every one of the radar elements, part of the circuitry was this very large, very high precision resistor that dumped a lot of heat under certain circumstances. It was a thick film ceramic resistor that was cooled. The problem is they were making it using the traditional screen printing. And what they were doing was print, dry, print, dry, print, dry, and then fire. And on a single to make, very thick, and they were, had all the right materials. So the problem was when you do that, your manufacturing process is really not very optimal. Screen printing, when you do multi-layers like that, is not all that controllable. So their yields were extremely erratic and consistently in the single digit percentages. And these were very expensive components, and they were having real problems even getting enough of them to fulfill their requirements for the Navy program. So somebody basically contacted the professor, probably through his university contacts, and so he came to us to basically say, well, these guys want to do some experiments. Can you use it? So they did the experiments with our system, and then later they bought their own system because what they found was this system was almost ideal. They're only doing the one screen, right? They're only doing the one ink, and the ability to write the ink at the correct thickness and do it under precision control. It was an ideal solution, right? And so they went from a few percent to very high percentage, solved their problems. They had a manufacturing solution that worked. And so essentially a big roadblock in the program was broken through and they moved forward. So essentially this was a huge win as far as the Navy was concerned and solved a many $1 million problem very, very effectively. For a power resistor, one ink's fine, no material switching, no CAD needed. The material saving was irrelevant because you weren't changing materials. It's one pass, real time, and they had their own engineers and they basically worked through the problem. It was an ideal kind of a solution. And, they basically, that was all solved through a very kind of old-fashioned, instead of the company going and selling or any of that, basically the engineering network found the solution that they were looking for and implemented it and brought the whole thing together. They bought, I think, several machines, and they went forward and it got what they needed. So it's often who you know, not what you know, which is very important. I mean, the other thing is though this program, as of when I left the government, and we had never made it beyond the phase two. In fact, I had worked with the son of the professor who had died during the early phases of the demoing with the Navy program. Um, I worked with his son looking for phase three. I talked to the contractor to see if we could get them to basically sponsor a phase three effort. And the reality is they were there to solve a problem. They weren't there. The problem really is we needed to have software development. We needed a multi-head system, all that. They weren't up for doing that. That wasn't really what they were there for. And they didn't need it. And so we were working on things, but again, my involvement faded away because the organization I worked for was basically done away with by Congress because they didn't like, the contractors didn't like having experts in the government who understood some of the stuff that they brought forward wasn't always the best stuff. You can really look at this as a failure from an SBIR matrix. The company did sell multiple machines into very specialized applications, but not very many. And it never went to phase three. I don't think it ever did. But the reality is from the Navy's viewpoint, the Navy probably saved multiple tens of millions of dollars over time with the solution. And really, when you look at it, it's a failure as far as the bureaucratic accounting is. But if you look at it more from a kind of a VC funding thing, it was a success, right? The reality is that, okay, it didn't succeed on the metrics that it was originally intended to solve, but it solved this other problem, and that was a breakaway success, and that was great. And that's how VCs operate, right? They operate on the thesis that, as long as yes, this idea looks like it's great and it makes sense, let's go for it. And they know that they're going to fail 9 times out of 10. Something's going to go wrong, but they know that 1 time out of 10, it's going to work fine. But they also know that 1 time out of 100, one of them is going to succeed in ways they probably never really anticipated. And that's where they often make their real money, is in areas where it succeeds in ways that were not expected. So there's a real dichotomy between what is a success and a failure when you look at it from a bureaucratic tick the box viewpoint versus a what did I do to help the overall progress of, the system, overall system going forward. So, it was very unfortunate Professor died. He was a great guy. We tried to carry it forward. I think the company, was probably okay. I think they actually kind of transitioned to do other things with their own equipment. So they kind of made a success out of it, but it is what it is as far as that's concerned. It didn't work quite the way it was originally anticipated, but it had its own strengths, and it moved into those strengths in ways that were not originally. But whether it was a success or a failure is entirely on your view of what that means. And are you ticking a box that was established, or are you saying, okay, treat it as its own thing and say, yeah, it was a real success, and it earned all of that on its own. So that's the story for this week. I'll be back. I'll probably be talking a little bit about being on the other side next week, and some of the issues to do with, why people sometimes complain about the SBIR, etc. But that's for next week. So this was the Unretired Engineer. I hope you enjoyed this. If so, you know what to do. I will come back at you in a week or so. Cheers.